Okay, welcome back everybody. We're going to start with this do now and try this problem. And if you don't remember what features a GEO satellite have, you should go back and read that excerpt from the last notes from Richard Muller's book about satellites. Okay, so pause your video and do this problem. Okay, here's my solution, and I started with the free body diagram. There's the object, the satellite, and here's the Earth. And it's assuming it's a circular orbit. The equation is net force equals mv squared over r. Solve for v, and you get square root of gm over r, where r is the radius of the orbit. So we have to be really careful, because when we're using this equation, the universal law of gravitation, r refers to the distance between the centers of the two objects. So the center of the satellite, the center of Earth, that distance. And when we're using this equation for circular motion, r refers to the radius of the circle. So that's the distance from the center of the circle to the orbiting object. So this works. To say these are the same, that works if the satellite has small mass and the Earth is basically not moving or wobbling. But once you get a larger satellite, or a more extreme example would be the binary star problem we're going to do later, where they're definitely the R's are definitely different when you have a larger satellite. We'll see that later. Okay, but now we're making this assumption they're the same. And just to remind you that when we talk about that R, that's the sum of two distances, the radius of the Earth plus the radius of the altitude. Okay, we're calling it R right now. We also know that the velocity is equal to the distance over time, circumference over period. Solve for period, and substitute the other equation we got for v, and you get this expression. And then solve for r, and you get this expression. And then recall that for a GEO satellite, the period is 24 hours. So we can put that in, solve for r, we get this radius, and then if you subtract the radius of the Earth, you get the altitude. Okay, so today we're going to go over the 4 FRQs that were due, that you're going to do over break. And then I'm going to tell you about Newton's shell theorem, which is a new one of the few theorems we have in this class. And then I'm going to tell you about elliptical orbits. Okay, let's go over the 4 FRQs we have. Okay, I'm just going to show you my solutions to these, and you can look at the published solutions from the College Board. But thought it might be helpful for you to see the way I did it, which is pretty similar to what they did. And I'm going to go through these pretty quickly. So this, the one thing about this glider is the glider is pulled at first, and then when it's released, it goes and it's being pulled by the spring. So you have a situation where it starts with spring potential and then has kinetic later when it's not being pulled, when the spring's not pulled anymore. And you're plotting these things so that you can find a best fit line and find the slope, and use the slope to find this k over m, which from the equation you wrote before, that's the slope of v squared versus x squared line, and use it to solve for m. So we've done this kind of thing before, and you should be comfortable with this. And then if you have it at an angle, the only difference is that you have this gravity term, and you have to notice that it's not just h, it's h plus x sine theta. Okay, so going to the next one. On this one, you've got a rotating platform. And I started with a free body diagram for this circular motion, wrote an equation, it's spring force equals mv squared over r, and solve for the spring constant. And that's what I got. And then solve for the rotational inertia, which is just a point particle, mr squared. And then we know that the rotational inertia of everything is the sum of those, and it ends up being this. For each of these, you just need to make sure that everything is in terms of the given variables. Super important. Okay, and then angular momentum is I omega. You can do that. All right, and then we have a new location. It's still circular motion, similar expression, and solve for the stretch distance there. Okay, and then it's asking about what happens if let's see, hold on, later the rod keeps moving, but what's happening here? Sorry. Let me just pause this. Okay, sorry. So I thought the rod was still moving towards the axis of the platform. So it's moving in, and you can see that because these two are decreasing moment of inertia, so overall the angular momentum is decreasing. Okay, and finally, you have negative work because your rotational inertia is decreasing and your angular velocity is the same. I think that's pretty straightforward. If you have decreasing kinetic energy, then you know your work is negative. This last one is pretty interesting, and here's my explanation of it. At first glance, you might think it just has acceleration towards the center, but actually because the angular velocity is staying the same, but the radius is changing, the linear velocity is decreasing, and so there is a component of acceleration that is to the right. And I'm showing that here, and then here's the resultant. Okay, so on the next one, this is a torsional pendulum. This one is a good example of writing a differential equation, and here it is. Starting from the torque equals I alpha equation. And then solving that differential equation gives you the period, or gives you omega. The solution to this differential equation, just like this one, is a sine function. So for both of them, it's a sine function. Okay, again here we're graphing t squared versus I, and use the slope of the line. Again, if you use these points, it's going to be marked wrong because you can see these don't give you the same slope as the line itself. So they make sure that you're actually using points on the line. Find the slope and use that slope to find b, because the slope is equal to 4 pi squared over b. So that's the idea here. And the last one is a physical pendulum. So I didn't say much about this in class, but this is a negative restoring force because it's going in back towards the center. So when it's restoring, it's negative. And so that might be the one thing that you didn't know. And then here's the small angle approximation. Sine theta is basically equal to theta. And now this looks just like the kind of equation we've seen where the second derivative of theta gives you theta again. And so it must be a sine function, in other words, and so then you can find omega and you can find t. Okay, so just the last part is describing an experiment. How would you find t? And then how would you find the center of mass? Okay, and you know how to do that. Okay, and that's that. Okay, here's a quick note for you about the Hewitt worksheets. Just to note that when it talks about 8 kilometers per second, we derived that last class, so look that up, but that's the speed of a satellite orbiting basically at the surface of Earth or close to it. And so that's your minimum orbital speed for a satellite. Okay, this is Newton's shell theorem, and you're going to need it for next class. So let me tell you what this means. Okay, so think about this thin, uniform, spherical shell. You could think of it as a hollow sphere. What kind of force does it exert on this point particle over here? And you can see that this side of the shell exerts less force because it's farther away according to the gravitation equation. And this side exerts more force because it's closer. But on average, the whole sphere exerts the same amount of force on this particle as if all of this mass was located at its center. So I think you can kind of see that. Then if you look, this one's more interesting. If you look at a sphere with the point particle on the inside, and what force does this mass exert on this point particle? We'll first look at the case where the point particle is in the middle, and you'll see that all the mass exerts equal force in all the directions, and so all those forces cancel out, and there's zero force acting on it. And it turns out no matter where you put the point particle within this sphere, the total force will be zero. For example, if you put it closer to this side, you have more force, but less mass exerting that force, whereas the other side of it has more mass, but it's farther away in general. And so it turns out if you do some calculus on this, you'll find that the total force adds up to zero, no matter where you put the point particle within the sphere. So that's Newton's shell theorem. Okay, now we're going to talk about, we've been talking about circular orbits, but we're going to talk about elliptical orbits a little bit. And I want to show you the definition of an ellipse. So here I have a string, which is a fixed length because it's a loop. And so the sum of the two parts going to the outer circle is always a constant value. See that? The sum of the two strings, the center string isn't changing, so the sum of the two others, it always adds up to a constant. And that's the definition of ellipse. And these are the two foci of the ellipse. Okay, please go to this link and watch this Hewitt video. It's 3 minutes long, and see if you can answer these questions. Do that now. Okay, so here are some notes on the elliptical orbit. If it was a circular orbit, which it would be if both of the two foci, or the two focus and the other focus, if they were at the same location, this would be a circle. That's a special case of an ellipse. And in that case, it would be circular motion, and you could say it equals mv squared over r, and then you could solve v equals square root of g m over r, which we've done before. But the radius keeps changing, and so v is not constant. V is changing, and that's an important feature of an elliptical orbit, which, by the way, every orbit in the universe of planets and moons and comets, they're all elliptical, or maybe they're the special case of circular. Every orbit is elliptical, and that means its velocity is changing. In fact, the velocity is increasing as it gets closer to the thing it's orbiting, and decreasing as it's going away. By the way, there's nothing at the other focus. The thing it's orbiting is at one of the two foci, and there's nothing at the other focus. That gravitational force is what increases the velocity, as Hewitt said, and then it decreases it as well because it's pulling against the direction of velocity, slowing it down. So you can see, by the way, apoapsis means the farthest point. Periapsis is the closest point. If it's orbiting the sun, you talk about the aphelion and the perihelion. If it's orbiting the moon, it's apolune and perilune, etc. But apo and peri is what you should remember. And then at that point, it has minimum velocity, so minimum kinetic energy, but it has maximum potential energy. In fact, the total energy is constant, and that's what I want you to see, that energy is conserved in this kind of a elliptical orbit. And not only is energy conserved, as Hewitt mentioned, momentum is also conserved. And you can recall the momentum of a point particle is mrv, and because it's I omega, we've done this before. And so at the apoapsis, v is a minimum and r is a maximum, right? Maximum radius, minimum velocity. Periapsis, v is a maximum, r is a minimum, but the mrv is a constant. This product is a constant. And so the angular momentum is a constant. And that's pretty useful. Let's do an example. Pause your video and try this problem. Pause it now. Okay, here's my solution to that problem. You can look at the data yourself and check how it's done. You just need to know that the perihelion has the max velocity, the aphelion has the minimum. Okay, check it. And that's it for today. Thank you.